Welcome to the next episode. This is Hirendrada, and in this video, we are going to look at Prelab 6 solutions guide for EE361. So let's look at lab number 6. Okay, lab number 6 is logic gates, flip-flops, and a simple counter circuit. So first thing we have to know is, well, in the digital realm, everything is using the binary number system, right? We're talking about electronic devices which can only understand high or low. So in terms of voltages or signal levels, a high signal is 5 volts and a low level is 0 volts. Now, let's go here. So again, I was saying logic gates are basic building blocks for digital systems. They work on the binary number system of zeros and ones, okay? Either a switch is on or a switch is off. In terms of circuit analysis, this would be 5 volts, this would be 0 volts. So a system that has plus 5 volts is said to be logic high or 1. So 1 is logic high and 0 is logic low. And based on these, there are many different circuits that you can that can be used to build digital systems. The primary logic operations, the three primary logic operations are the AND, OR, and NOT. And basically, these gates are made out of transistors, like BJTs, MOSFETs, so the transistors that we have already learned. And they each serve a specific purpose. So here, F notes the output of each one of these gates, and A and B represent the input. So an AND operation is basically A times B. A OR operation is A plus B. And a F NOT operation is basically an inverter. So a NOT is basically an inverter, meaning if you give a logic low signal as input to a NOT gate, the output F is logic high. And if you give logic high, then the output is logic 0 or logic low. Now, this symbol right here stands for NOT, right? A NOT. Now, based on the operation, the mathematical operation, even though it seems like it's simple algebra, it is not. It's a different kind of algebra. So logic algebra is known as Boolean algebra. And based on that, we come up with the functionality of each gate. And we sum up or summarize this in something known as the truth table. Okay, truth table. So the truth table for AND gate, depending on how many inputs we have. In this example, we have 2 inputs. If you have 2 inputs, they can only take 4 combinations. So each input can take only a 0 or a 1. And so based on that, we have 0, 0, 0, 1, 1, 0, and 1, 1. Now an AND operation, 0 times 0 gives us 0, 0 times 1 gives us a 0, 1, 0 gives us a 0, and 1, 1 also, 1, 1 gives us a 1. Now XOR, not XOR, OR gives us a summation operation. And so anytime any of the input is high, the output also is high. For an AND operation, both outputs or both inputs must be high in order for the output to go high. Okay. A NAND gate or a NOR gate is simply an AND or a OR gate connected to a NOT gate. So here it says plus, but what it means is basically you take the output of the AND gate and connect it to a NOT gate. So the truth table for a NAND gate and a NOR gate is the exact opposite of the AND and OR gates. Okay, AND and OR gates. And then we have something known as the XOR gate. The XOR gate stands for exclusive OR gate. And the symbol is given by this. So A plus B with the A inside a circle is also a modulo 2 addition. And modulo 2 addition simply means that the output of the XOR gate goes high when either one of the input goes high. When the inputs are the same, the output goes low. So output for the XOR gate is low when inputs are the same. And XNOR is basically the output of XOR fed into a NOT gate. So it's the exact opposite of the XOR gate. So from these things, hopefully students will be able to write out the truth table for the required question. So the required question is right here. It simply asks you to draw the logic symbol and construct the truth table for a NAND, NOR, and XNOR gate. And as always, of course, the background section does give you a little bit of, not a little bit, a lot of the information that you need. Okay. Now, the symbol for a NAND gate is shown right here. And in the Prelab guide, right here, I have shown you the symbols for a AND, OR, and a NOT gate, and also for the exclusive OR. Okay. Now, whenever you have a NAND, NOR, or XNOR, meaning the output of a simple gate is fed into a NOT gate, well, the NOT gate is indicated by a bubble. So there's a bubble right here at the output. Okay. So if you want, for example, refer to a NAND gate, the output for a NAND gate will be like a AND with a bubble. And so the NOR gate is similar, and the XNOR will also be similarly done. You simply have to add a bubble at the output. The bubble indicates a NOT operation. Okay, let's take a look at, well, that was question number 1. Let's take a look at question number 2. So question number 2 asks you to write the truth table for a RS flip-flop. RS flip-flop. Now, a RS flip-flop stands for set reset or reset set. But typically we call it a set reset flip-flop. So an SR flip-flop is a logic circuit that can store data, right? It stores zeros and ones. And when we mean storage, meaning the input can change, but the output will not. Okay, so that's what it means by storing the data. And so here the circuit shows a cross-coupled NAND, two cross-coupled NAND gates. One of the inputs of each of the NAND gates is tied to the other gate's output, and the other inputs are labeled as set and reset. Okay, they're completely identical to each other. So if you call one gate as set, then the output of that gate is Q, and the reset output, the output is known as Q naught. Okay, Q naught. Typically, when you have a Q and a Q naught output in a flip-flop, it simply means that the values of both are opposite. Meaning if Q is 0, then Q naught is 1. And if Q is 1, then Q naught is 0. So let's see how you would analyze this circuit. The question being asked is to actually complete the truth table. Now the answer is of course in here, but let me explain how we arrive at that answer. So if we take a look at the circuit, we take a look at the truth table for a NAND gate. Now the truth table for a NAND gate is not given here, but as you can see from the truth table for an AND gate, the output of a NAND gate would go high if any one of the inputs is low. right? The NAND gate would be exactly the opposite of an AND. So the output of a NAND gate would go high when any input is low. Okay, any input is low. So let's say, for instance, S is equal to 0 and R is equal to 0. Well, for NAND gate, if any one of the inputs is low, the output goes high. So Q and Q0 are both high. Well, that's the thing about this flip-flop. We cannot have Q and Q0 high at the same time. Then a flip-flop output is ambiguous. And hence, if you look in the lab guideline, it tells you why. It tells you that for S and R both 0, 0, outputs Q and Q0 state of 1 and 1 is ambiguous. Okay, it's ambiguous. Let's look at what happens when S goes low and R goes high. So if S is low and R is high, what happens here? Where output of S, Q is still 1. So the input here is 1. And if that's 1, then Q0 goes to 0. And so that's the second line, second row in the truth table, in which you can see right here. When S is 0 and R is 1, Q goes to 1, Q0 goes to 0. You would analyze similarly for S is 1 and R is 0. Okay. Now, in the Prelab, when S is 1 and R is 1, in the Prelab, the question being asked is this, right? I showed you 0, 0, I showed you 0, 1. You can find out 1 and 0, or explain to yourself at least 1 and 0. Here in fourth and fifth state, both of them deal with S and R are both 1 and 1. But we have to account for both cases, meaning when R is 1 and S is going from 0 to 1, and when S is 1 and R goes from 0 to 1. Okay, so 1 and 1 can occur from both steps 2 and 3. If you were already at step 2, you're going from 0, 1 to 1, 1. And if you were at step 3, you're going from 1, 0 to 1, 1. Okay, so let's see what happens when we do that. Okay, so if we are already at S is 0 and R is 1, our outputs are Q as 1 and Q0 as 0. Now, if S goes to 1, what happens? This goes to 1. This is already 0. Well, it actually does not matter what happens here, because the output will always stay at 1. Okay. So once again, when the input was 0, 0 and 0, S was 0 and R was 1, my output Q is 1 and Q0 is 0. Okay, Q0 is 0. So if Q0 is 0, that is being fed into the input terminal of S, the S gate. So it doesn't matter what the input is at the other terminal, my output Q will stay at 1, meaning there is actually no change. There is no change in the state of that flip-flop. So it remains the same as the previous state. And that's why it is a storage flip-flop, meaning when both S and R go to high, the output of the flip-flop remains in a storage state. And hence you have the X marked over here. But in your Prelab solution, you cannot have XX. You have to show which state you're coming from. Okay, so in the question, step number 4 tells you that your previous state was 0 and 1. You're now transitioning from step 2, from 0 and 1, you're going to 1 and 1. Okay, So your answer for this Q and Q naught should come from step 2. Same thing for step 5. Step 5, input S is 1 and R is 0. So that is step 3. You're going from step 3, 1 and 0, you're going to 1 and 1. So your answer for that has to come from step number 3, which you should analyze and figure out for yourself. Okay, that's how you would solve for the truth table of a SR flip-flop. Okay, SR flip-flop. Now, third question, you have a 2-bit JK flip-flop. 2-bit because each flip-flop can store 1 bit. And so you have 2 of them. So it's a 2-bit JK flip-flop. If you take a look at the inputs J and K, they are both connected together and they're both connected to +5 volts, meaning logic high. Okay, so all inputs of both J and K of both JK flip-flops are connected to logic high. When that happens, you can look up the truth table for a JK flip-flop. The truth table for a JK flip-flop tells you right here, when J and K are both high, the output simply toggles. And toggling means if the output was 0 previously, it now goes to high. If the output was high, then it now goes to 0. Okay, so every clock input that's applied, J and K, if connected to high, will simply toggle for every clock input. Okay, so now let's take a look at the clock input that's given to us here. Now, V in signal is going directly into the CLK input, and CLK clock is given to us as rectangular pulses right here. We are asked to find what the outputs of Q1 and Q2 are going to be. Well, output Q1 is basically the output of the first JK flip-flop, and output Q2 is the output of the second JK flip-flop. In addition, output Q1 is connected as the input to the clock of the second flip-flop. Okay, so the output Q1 that we derive here is going to act as the clock for the second one. Now, a couple of things over here. You see there is a bubble right at the output or at the input of the clock. When there is a bubble, the input is actually a clock naught, meaning when V in goes 0, the actual clock in there goes high and is activated. Okay, so the flip-flop is said to be negative triggered, meaning whenever the whenever the CLK input goes low, that is when the flip-flop will actually work. Okay, that is when the flip-flop will actually work. And when it works, you know that the output is going to toggle from its previous state because J and K are permanently connected to +5 volts or logic high. That's the first thing. Second thing is clear. Clear, CLR, is also defined as the naught over here and it has a bubble end. Now there is no specific clear signal given to us here, but the assumption would be that clear is applied, and when clear is applied at the beginning state, the outputs of both flip-flops are 0, 0. Okay, outputs of both are 0, 0. So with those assumptions made, let's go and draw out our outputs. So we have edge triggered, can be both positive and negative, but here in our flip-flop, we have a bubble. Remember, there's a bubble in front of the CLK input. If there's a bubble, it means that the flip-flop is triggered when the clock signal goes low. Okay, so here we can see the clock signal goes high and here it goes low, right? It goes high here, it goes low here, and so on and so forth, right? So it goes high and it goes low. Since this is a negative triggered flip-flop, every time it goes low, it toggles the state. Now, output Q1 was already low. Output Q1 was already low, which means 0. Same thing with Q2. stays low. Now, when the first low going trigger arrives, that's when the output toggles. So the output goes high. The output stays high until the next trigger arrives, on which it goes low. It stays low until the next clock pulse arrives, whereupon it again goes high and then again goes low. And hope that makes sense. And from this, now consider that this Q1 is the clock signal for Q2. And if Q1 is the clock signal for Q2, you use the same application, same logic that I just described to determine Q1 to determine Q2. Okay, and that would be your output for Q1 and Q2 JK flip-flops. Well, that's it. That's the 3 questions for Prelab number 6. If you have any questions, please feel free to reach out to me. Email is hstrada@calpoly.edu. I will see you in the next video for Prelab number 7.